13. Why the solar system is tilted 6 degrees to the galaxy. Hello there, and welcome. Tonight I want to take you somewhere special, somewhere quiet and vast, where the questions we ask don't demand immediate answers, but instead invite us to wonder. I want to take you to a place where you can rest your mind while we explore together one of those beautiful mysteries that sits right at the edge of our awareness, something so fundamental we rarely think to question it. It's about the way our entire solar system, this magnificent collection of planets and moons and countless smaller bodies all dancing around our sun, leans ever so slightly in space. Yes, you heard that right. Our cosmic home has a gentle tilt, about 6 degrees from what we might expect, and tonight, as you settle in wherever you are, we're going to explore why that might be. But before we drift into this cosmic contemplation together, I'm curious about you. Where are you listening from right now? What time is it where you are? Perhaps you're tucked into bed, the day's concerns slowly dissolving as you prepare for sleep. Maybe you're in a different time zone entirely, finding a moment of peace in the afternoon or early evening. Wherever you are, whenever you are, you're part of this journey now. And if you find this gentle exploration of space and wonder helps you relax, if it becomes a companion to your quiet moments, consider subscribing so we can meet here again, unhurried, ready to explore more mysteries of our universe together. A simple like helps others find this peaceful corner of contemplation too. But for now, just settle in, take a deep breath, and let's begin. You know, it's a question that might seem too simple at first, almost trivial even. Why would it matter that our solar system is tilted 6 degrees? But that's the beautiful thing about the universe. The simplest questions often open the deepest doors, and this particular door leads us to the very birth of our solar system, to the nature of gravity and angular momentum, to the dance between our local neighborhood and the vast galaxy we call home. It's a question that touches on how we measure things in space, what we mean by up and down in a cosmos that has no absolute directions, and how the smallest variations in initial conditions can leave signatures that last for billions of years. What if this 6-degree tilt were like a fingerprint, unique to our solar system, telling the story of where we came from and how we got here? What if it were a whisper from our beginnings, a memory folded into the very fabric of space itself, waiting patiently for us to notice and wonder about it? Tonight, we're not rushing toward any definitive answer. Instead, we're going to explore the possibilities, the measurements, the theories, letting each one wash over us like gentle waves, building our understanding layer by layer, never forcing, never hurrying. Consider for a moment how remarkable it is that we can even detect such a subtle tilt. We're talking about 6 degrees. If you hold your hand flat and tilt it just slightly, barely enough to notice, that's roughly the angle we're discussing. And yet, this small lean affects everything in our solar system, from the way planets orbit to how we observe the galaxy beyond. It's present in every sunrise, every seasonal change, every celestial alignment we've ever witnessed. We've been living with this tilt our entire existence as a species, and only in recent centuries have we developed the tools and understanding to measure it precisely and ask why. The story of discovering this tilt is itself a journey through human curiosity and ingenuity. Ancient astronomers noticed that the planets seemed to move along a particular path in the sky, what we now call the ecliptic. They observed that this path was different from other celestial reference points, though they couldn't have known they were detecting the first hints of our solar system's orientation in space. It wasn't until we began to understand that we're part of a galaxy, that the Milky Way isn't just a band of light across the night sky, but our cosmic city of hundreds of billions of stars, that we could even frame the question properly. And here's where it gets even more interesting. The 6-degree figure isn't even the whole story. Depending on what we're measuring against, the plane of Earth's orbit, the average plane of all the planets, or the plane of the galaxy itself, we get different numbers. Each measurement tells us something different about our place in the cosmos. The 6 degrees we're focusing on tonight refers specifically to the tilt between the sun's equator and what we call the invariable plane of the solar system, that averaged out plane defined by the angular momentum of all the planets combined. But when we look at how our entire solar system is oriented relative to the galaxy, the angle is much larger, about 60 degrees. It's like we're a dinner plate spinning at an angle on a lazy Susan that's itself tilted on a table. Perhaps you're already feeling the gentle vertigo of trying to imagine these nested references frames, these planes within planes, all slowly turning at different rates and angles. That's perfectly natural. Our minds evolved to navigate a world where up and down seem absolute, where the horizon provides a clear reference line. But in space, every reference frame is relative, every up is someone else's sideways, and what seems tilted from one perspective might seem perfectly aligned from another. This isn't confusion, it's freedom. It's the universe inviting us to let go of our assumptions and float for a while in the actual reality of how things are. As we settle deeper into this contemplation, imagine yourself rising slowly above Earth, above the solar system, until you can see the Sun and all its planets as a single, slowly turning system. From this vantage point, you might notice that the planets don't all orbit in exactly the same plane. Each has its own slight inclination, its own individual tilt, though most are within a few degrees of each other. Mercury, the innermost planet, has the largest tilt at about 7 degrees from the average. Venus, Earth, Mars, Jupiter, Saturn, they all dance close to the same plane, with variations of just a degree or two. And then there's Uranus, rolling on its side at an extreme angle, and Neptune with its own moderate tilt, and beyond them the dwarf planets like Pluto with even more dramatic inclinations. Yet despite all these individual variations, there's a remarkable coherence to the system. The major planets, especially the giants like Jupiter and Saturn, dominate the angular momentum budget. Their massive presence defines that invariable plane we mentioned, that average plane that represents the system's overall orientation. And it's this plane, this collective average, that we compare to the Sun's equator to get our 6-degree tilt. The Sun, our local star, the body that contains 99.86% of all the mass in our solar system, doesn't quite spin in the same plane that its planets orbit. It's as if the conductor of an orchestra is swaying to a slightly different rhythm than the musicians, though the music remains harmonious. This might seem like a flaw, an imperfection in what we might expect to be a precisely aligned system, but perhaps it's more beautiful this way. Perhaps perfect alignment would be the anomaly, the thing that would require explanation. After all, when we look at other star systems, and we've now observed thousands of them, we see tilts and misalignments everywhere. Some are dramatic, with planets orbiting backwards or at wild angles to their star's rotation. Others show the same kind of gentle lean we see in our own system. It seems that tilt, misalignment, asymmetry, these aren't bugs in the cosmic code but features, natural outcomes of how solar systems form and evolve. Think about this for a moment. Every solar system we've studied shows some form of misalignment. This tells us something profound about the universe. Perfect symmetry is the exception, not the rule. The universe prefers a little chaos mixed with its order, a little jazz in its classical composition. And our 6-degree tilt, it's our solar system's particular note in this cosmic symphony. Neither too dramatic nor too subtle, just enough to make us unique while still being part of the universal pattern. The question of why our solar system is tilted can't be separated from the question of how solar systems form in the first place. Picture, if you will, a vast cloud of gas and dust floating in space, perhaps several light years across. This cloud, what astronomers call a molecular cloud, is mostly hydrogen and helium, with traces of heavier elements, the ashes of previous generations of stars. The cloud is cold, incredibly cold, just a few degrees, above absolute zero, and it's not uniform. There are denser regions and more diffuse regions, areas where the gas swirls one way, and areas where it swirls another. The cloud as a whole might be rotating slowly, almost imperceptibly, taking millions of years to complete a single turn. Now something happens to disturb this cloud. Perhaps a nearby star explodes in a supernova, sending shock waves rippling through space. Maybe the cloud passes through a denser region of the galaxy, feeling the gravitational tug of extra matter. Or possibly the cloud simply reaches a critical point where its own gravity overcomes the outward pressure of its cold gas. Whatever the trigger, parts of the cloud begin to collapse, and as they collapse, something remarkable happens. They begin to spin faster. This is conservation of angular momentum in action, the same principle that causes a figure skater to spin faster when they pull in their arms. But here's the crucial part. The collapse isn't perfectly symmetrical. How could it be? The cloud wasn't uniform to begin with. Different parts were already moving in slightly different directions, had slightly different densities, slightly different temperatures. As the collapse proceeds, these small differences get amplified. Material falling in from one direction might have a bit more angular momentum than material falling in from another direction. Magnetic fields threading through the cloud, yes, even these vast diffuse clouds have magnetic fields, can channel the infalling gas in particular ways, adding their own twist to the collapse. Within this collapsing region, a star begins to form at the center where the density is highest. Around it, the infalling material that has too much angular momentum to fall directly onto the star instead forms a disk, what we call a protoplanetary disk. This disk is where planets will eventually form, but already, even at this early stage, we can see the seeds of misalignment. The star's rotation axis might not perfectly match the disk's rotation axis. The inner parts of the disk might be tilted relative to the outer parts. Magnetic fields connecting the young star to its disk can transfer angular momentum in complex ways, causing the star to tilt relative to the disk or vice versa. Recent observations by the Atacama Large Millimeter Array, or ALMA, have shown us these baby solar systems in unprecedented detail. And what we see is fascinating. Many of them show misalignments right from the start. We see disks that are warped, twisted, or broken into distinct planes tilted relative to each other. We see young stars whose rotation axes don't match their disks' orientations. It seems that the 6-degree tilt we observe in our mature solar system might have its origins in these very earliest moments, when our sun was still gathering itself from the cosmic cloud. But the story doesn't end with the initial formation. Over millions of years, as planets begin to form within the disk, they engage in their own complex dance of gravitational interactions. Large planets like Jupiter can migrate inward or outward, disrupting the orbits of smaller bodies. Planets can scatter off each other, changing their inclinations and eccentricities. The disk itself evolves, with gas being blown away by stellar winds and radiation, changing the gravitational landscape in which the planets are forming. Each of these processes can add to or modify any initial tilt, creating the final configuration we see today. And then there's the possibility of external influences. Our sun wasn't born alone. Stars typically form in clusters, sometimes with hundreds or thousands of siblings, all born from the same giant molecular cloud. In these stellar nurseries, young stars can pass relatively close to each other. Not close enough to collide, but close enough for their gravity to affect each other's forming planetary systems. A close pass by another star could tilt a protoplanetary disk, or strip away some of its outer regions, or even capture or eject forming planets. By the time our sun left its birth cluster and began its solitary journey through the galaxy, it might have already acquired its characteristic tilt through one or more of these encounters. There's something deeply moving about this idea, that our solar system's tilt might be a memento from our sun's youth, from a time when it had stellar siblings nearby, when it was part of a community of young stars all beginning their long lives together. Most of those siblings are now scattered across the galaxy, too far away for us to identify. But perhaps, in our 6-degree tilt, we carry a memory of them, a subtle reminder that even our sun, now travelling through space with only its planets for company, was once part of something larger. As we contemplate these possibilities, it's worth pausing to appreciate the extraordinary precision with which we can now measure these cosmic angles. The 6-degree tilt between the sun's equator and the invariable plane wasn't something astronomers could just eyeball. It required careful observations of sunspots to determine the sun's rotation axis, precise tracking of planetary positions over many years to establish the invariable plane, and sophisticated mathematical models to bring it all together. The number itself, about 6.23 degrees if we're being precise, represents the culmination of centuries of astronomical observation and decades of space-age measurements. Consider what it means to measure an angle in space, where there's no horizon, no up or down, no fixed reference point. We have to create our own references, build our coordinate systems from the movements of celestial bodies themselves. The ecliptic, the plane of Earth's orbit around the Sun, becomes one reference. The invariable plane, defined by the total angular momentum of the planetary system, becomes another. The galactic plane, that vast disk of stars we see edge on as the Milky Way, provides yet another. Each of these planes is defined by motion, by the accumulated paths of objects moving through space over vast spans of time. And here's something beautiful. All of these reference planes are themselves in motion. The ecliptic processes slowly due to gravitational perturbations from other planets. The invariable plane shifts slightly as the planets migrate and their orbits evolve. Even the galactic plane isn't truly fixed. It warps and ripples like a flag in a cosmic breeze. We're measuring angles between moving references, like trying to determine the angle between two carousel horses while riding on a third. The fact that we can do this at all, that we can extract these stable, meaningful numbers from this cosmic dance, is a testament to both the underlying order of the universe and the power of human intellect to perceive that order. The measurement of the sun's tilt relative to the planetary system also tells us something about the sun itself. Our star rotates once every 25 days at its equator, but this rotation isn't uniform. The sun rotates differentially, faster at the equator than at the poles, taking about 35 days to complete a rotation at high latitudes. This differential rotation is possible because the sun isn't solid. It's a giant ball of plasma, with different layers and latitudes free to rotate at different rates. And this complex rotation pattern generates the sun's magnetic field, which in turn drives the solar cycle of sunspots and solar storms that can affect Earth. The tilt of the sun's rotation axis means that over the course of a year, we see the sun from slightly different angles. Sometimes we're looking more at the sun's north pole, sometimes more at its south pole. This changing perspective affects how we observe solar features like sunspots and coronal holes. It also means that the solar wind, that stream of charged particles constantly flowing from the sun, hits Earth from slightly different angles throughout the year. These variations are subtle, but they're part of the complex space weather system that surrounds our planet. When we expand our view to consider how our tilted solar system moves through the galaxy, the picture becomes even more interesting. The entire solar system is orbiting the center of the Milky Way at a speed of about 230 kilometers per second, completing one orbit every 225 million years or so, what astronomers sometimes call a galactic year. But we're not moving in the plane of the galaxy. Instead, we're currently about 55 light years above the galactic plane and moving upward at about 7 kilometers per second. Like a horse on a carousel, we bob up and down as we circle, oscillating above and below the galactic plane with a period of about 60 million years. This motion through the galaxy means that our solar system is constantly encountering new regions of space. We pass through areas of different density, different magnetic field strengths, different populations of stars. Some scientists have suggested that these passages might correlate with events in Earth's history, like mass extinctions or climate changes, though the evidence for such connections remains debated. What's certain is that our journey through the galaxy is not a simple circle, but a complex path, influenced by the gravitational pull of nearby stars, giant molecular clouds, and the spiral arms of the galaxy itself. The tilt of our solar system relative to the galaxy also affects how we see our cosmic neighborhood. Because we're tilted about 60 degrees to the galactic plane, we get a good view of both the northern and southern galactic hemispheres. If our solar system were aligned with the galactic plane, the disk of the galaxy would block our view of half the universe. Instead, our tilt gives us a relatively unobstructed view in many directions, allowing us to study distant galaxies and the large-scale structure of the universe. It's as if the universe arranged our viewing angle to maximize our ability to explore and understand it. Though of course, this is just a fortunate coincidence. There's something profoundly peaceful about contemplating these vast scales and slow motions. While our daily lives can feel hurried and chaotic, the cosmos operates on timescales that dwarf human experience. The sun's tilt hasn't changed appreciably in all of human history. The solar system's orientation in the galaxy shifts so slowly that constellations familiar to the ancient Greeks are still recognizable to us today. Even the fastest planetary orbits, Mercury circles the Sun in just 88 days, represent a kind of stability and predictability that we can count on absolutely. Yet within this stability there's also change, evolution, a story being told. The solar system we see today isn't exactly the same as it was when it formed 4.6 billion years ago. Planets have migrated, moons have been captured or formed, countless asteroids and comets have been scattered or ejected. The sun itself has grown slightly brighter over time and will continue to do so, eventually making Earth too hot for life as we know it, though that's still hundreds of millions of years in the future. The 6-degree tilt we observe today might not be exactly the same as it was billions of years ago, and it might be slightly different billions of years from now. This brings us to one of the most intriguing aspects of the tilt question. Is it changing? And if so, why and how fast? To answer this, we need to think about torques, forces that can cause rotation or change the orientation of a rotating body. In our solar system, there are several potential sources of torque that could, in principle, affect the Sun's orientation or the plane of the planetary orbits. The gravitational pull of the planets on the Sun's oblate shape. The Sun is slightly flattened due to its rotation creates a small torque. The gravitational influence of passing stars or molecular clouds could provide external torques. Even the galaxy itself, through its tidal forces, might have a subtle effect. But when astronomers calculate the magnitude of these torques, they find that they're incredibly small. Any change in the solar system's tilt would occur over timescales of hundreds of millions or billions of years. This is actually reassuring. It means our cosmic neighborhood is stable, that the stage on which life on Earth plays out isn't going to suddenly shift beneath us. The 6-degree tilt is, for all practical purposes, a permanent feature of our solar system, as unchanging as the mountains and as reliable as the sunrise. Some scientists have proposed more exotic explanations for the solar system's tilt. What if there's a distant, undiscovered planet in the outer solar system whose gravity has slowly torqued the Sun or the inner planets over billions of years? This hypothetical Planet 9, if it exists, would need to be several times the mass of Earth and orbit hundreds of times farther from the Sun than Earth does. While there's some indirect evidence for such a planet, certain patterns in the orbits of distant Kuiper belt objects that might be explained by a distant planetary perturber, it remains unconfirmed, and even if Planet 9 exists, its effect on the solar system's overall tilt would likely be small. Another possibility is that the tilt is primordial, dating back to the very beginning of the solar system, or even before. Perhaps the molecular cloud from which our Sun formed was already rotating at an angle to what would become the galactic plane, or perhaps the specific way our portion of the cloud collapsed, influenced by turbulence, magnetic fields and nearby stars, naturally led to a misalignment between the forming Sun and its disk. In this view, the 6-degree tilt isn't something that happened to our solar system, but something it was born with, as inherent to its identity as the number of planets or the composition of the Sun. There's a certain poetic beauty to this idea, that our solar system's tilt might be a fossil from before the Sun even existed, a geometric inheritance from the cosmic cloud that gave birth to everything we know. It connects us to the deep history of our galaxy, to the cycles of stellar birth and death that have been going on for billions of years before our Sun first began to shine. Every atom in our bodies, except for hydrogen, was forged in the nuclear furnaces of dying stars and scattered into space by supernovae. And perhaps the very orientation of our solar system, that 6-degree lean, is another kind of inheritance from our cosmic ancestors. As we continue our contemplation, let's consider what we mean by measurement itself in this cosmic context. When we say the solar system is tilted 6 degrees, we're making a statement that seems precise, scientific, objective. But every measurement carries with it assumptions about what we're measuring and why it matters. The 6-degree figure specifically refers to the angle between the Sun's equator and the invariable plane of the solar system. But we could just as easily cite other angles. The 7.25-degree tilt of the Sun's equator to the ecliptic, the roughly 60-degree angle between the invariable plane and the galactic plane, or any number of other angular relationships in our cosmic neighborhood. Each of these angles tells a different part of the story. The Sun's tilt relative to Earth's orbit affects the seasons on Earth and how we observe solar phenomena. The tilt relative to the invariable plane tells us about the angular momentum distribution in our solar system. The tilt relative to the galaxy places us in our larger cosmic context. There's no single true tilt. Each angle is true for its own purpose. Each reveals something different about our place in the universe. This multiplicity of perspectives isn't a weakness in our understanding, but a richness, a reminder that reality can be validly described from many viewpoints. This brings us naturally to the philosophical implications of cosmic tilt. In a universe where there's no absolute up or down, no fixed cosmic coordinate system, what does it mean to be tilted? Every tilt is relative to something else. Every angle implies a relationship between two frames of reference. In a sense, tilt is about connection. It's a way of describing how different parts of the universe relate to each other. Our solar system's tilt connects us to our galaxy. Our sun's tilt connects it to its planets. Earth's tilt connects us to the seasons and the cycle of life. Perhaps this is why the question of tilt feels so compelling, even though it might seem abstract or technical at first. We're not just asking about angles and planes. We're asking about relationships, about how we fit into the larger cosmic story. The 6-degree tilt is a thread that, when pulled, unravels into questions about the formation of solar systems, the structure of galaxies, the nature of gravity and angular momentum, and ultimately our place in the universe. It's a simple number that opens onto infinite complexity. As you listen to these words, perhaps feeling yourself beginning to drift towards sleep, consider how your own perspective is tilted right now. You're lying or sitting on the surface of a planet that's tilted 23.5 degrees on its axis, orbiting a star that's tilted 6 degrees from the average plane of the planets, in a solar system that's tilted 60 degrees from the galaxy, in a galaxy that's moving through space at hundreds of kilometers per second towards something called the Great Attractor. You're part of this vast, tilted, moving, evolving cosmos, and yet you're also perfectly still, perfectly at rest in your own frame of reference. This is the paradox and the beauty of our cosmic situation. We're in constant motion, spinning, orbiting, travelling through space at speeds that would seem impossible if we could feel them, and yet, from our perspective, we're at the calm centre of it all. The universe wheels around us even as we wheel through it. Every perspective is valid, every frame of reference is legitimate, and somehow in this relativity we find not chaos but order, not confusion but beauty. The instruments we've built to measure these cosmic tilts are themselves marvels of human ingenuity. Space telescopes like Gaia are mapping the positions and motions of billions of stars, allowing us to understand our place in the galaxy with unprecedented precision. Solar observatories like SOHO and the Solar Dynamics Observatory watch the sun continuously, tracking its rotation and magnetic activity. Planetary missions like Cassini, Juno, and New Horizons have refined our measurements of planetary orbits and orientations. Each mission adds another piece to the puzzle, another data point in our quest to understand why things are the way they are. But perhaps the most remarkable instrument in this investigation is the human mind itself. Its ability to conceive of these vast scales, to imagine perspectives far removed from our everyday experience, to find patterns and meaning in the cosmos. When we ask why the solar system is tilted 6 degrees, we're exercising a capacity that, as far as we know, is unique in the universe. The ability to step outside ourselves, to see our situation from a cosmic perspective, and to wonder about it. This wondering, this curiosity, might be the most precious thing about us. As we prepare to transition into exploring the deeper technical aspects of how we measure these cosmic angles, let's rest for a moment in the simple wonder of it all. Somewhere in space, right now our entire solar system is gliding through the galaxy at an angle, like a frisbee thrown slightly off level, maintaining its tilt as it goes. This has been happening for billions of years and will continue for billions more. The 6-degree tilt is both a mystery to be explored and a fact to be accepted, a question that leads to more questions, an answer that's beautiful in its simplicity. In the quiet depths of space, angles matter and don't matter, measurements are precise and approximate, and our tilted solar system continues its ancient dance. You're part of this dance, have always been part of it, will always be part of it. And as you drift towards sleep tonight, you can rest in the knowledge that you're held safely in the arms of gravity, angular momentum and time, cosmic forces that have maintained their steady rhythms since before Earth existed, and will continue long after we're gone. The tilt is just one note in this vast symphony, but what a beautiful note it is. Now, as we've established this foundation of wonder about our solar system's gentle lean, we need to explore more deeply what we mean when we talk about measuring angles in space. How do astronomers determine that something is tilted when there's no universal up to measure against? What exactly is this invariable plane we keep mentioning, and why is it so important? These questions will lead us deeper into the elegant mathematics of celestial mechanics, but don't worry, we'll keep our journey gentle, contemplative, always returning to the wonder that sparked our curiosity in the first place. The story of measuring celestial angles begins with a fundamental challenge. In the vast emptiness of space, there are no fixed landmarks, no absolute coordinate system waiting to be discovered. Everything is in motion relative to everything else. Earth spins on its axis while orbiting the Sun. The Sun moves through space relative to nearby stars. Those stars orbit the center of the galaxy. The galaxy itself moves through the universe. In this cosmic ballet of motion within motion, how do we even begin to define what's straight and what's tilted? The answer lies in choosing reference frames, artificial but useful constructs that allow us to describe positions and motions mathematically. Think of a reference frame as a stage on which we can describe the cosmic dance. We can choose different stages depending on what we want to observe. From Earth's surface, we use the horizon and cardinal directions. From Earth's orbit, we use the ecliptic plane. From the solar system as a whole, we use the invariable plane. From the galaxy's perspective, we use the galactic plane. Each frame is valid, each useful for different purposes, and the relationships between them, the angles of tilt, tell us something profound about how our cosmic neighborhood is organized. Let's start with perhaps the most familiar reference frame, the ecliptic. This is the plane of Earth's orbit around the Sun, or equivalently, the apparent path the Sun takes through our sky over the course of a year. Ancient astronomers noticed that the planets all appear to move within a narrow band centered on this path, never straying more than a few degrees from it. This told them something fundamental. The solar system is roughly flat, with all the major planets orbiting in nearly the same plane. The word ecliptic itself comes from eclipse. Lunar and solar eclipses can only occur when the moon crosses this plane, but Earth's orbital plane isn't the only possible reference. Each planet has its own orbital plane, each slightly different. Mercury's orbit is tilted about 7 degrees from Earth's, Venus about 3.4 degrees, Mars 1.8 degrees. The giant planets are all within about 2 degrees of Earth's orbital plane. If we want to describe the solar system as a whole, we need something more fundamental than any single planet's orbit. This is where the concept of the invariable plane becomes essential. The invariable plane is defined by the total angular momentum of the solar system. Angular momentum is a measure of rotational motion. It combines how fast something is rotating or orbiting with how massive it is and how far it is from the center of rotation. In our solar system, Jupiter, with its enormous mass and substantial distance from the Sun, contributes the lion's share of the angular momentum. Saturn comes second, and the other planets contribute progressively smaller amounts. The Sun, despite containing most of the system's mass, contributes relatively little angular momentum because it rotates slowly and its mass is concentrated near the rotation axis. When we add up all these angular momentum vectors, and yes, angular momentum has direction as well as magnitude, we get a total that points perpendicular to what we call the invariable plane. This plane is invariable because, barring external forces, the total angular momentum of the solar system is conserved. Individual planets can exchange angular momentum through gravitational interactions, but the total remains constant, and thus the invariable plane provides a stable reference that represents the solar system's overall orientation in space. The invariable plane is tilted about 1.58 degrees from the ecliptic, Earth's orbital plane. This might seem like a small angle, and it is, but it tells us that Earth's orbit isn't perfectly representative of the solar system as a whole. Jupiter's orbital plane is much closer to the invariable plane, tilted only about 0.3 degrees from it. This makes sense when we remember that Jupiter dominates the angular momentum budget. In a way, the invariable plane is Jupiter's plane, with small contributions from the other planets nudging it slightly. Now we come to the Sun's role in this geometric arrangement. The Sun rotates on its axis once every 25 days at its equator, and this rotation defines another plane, the Sun's equatorial plane. If the solar system had formed from a perfectly uniform, undisturbed cloud of gas, we might expect the Sun's equator to align perfectly with the invariable plane. After all, both should reflect the original angular momentum of the collapsing cloud. But observations show that the Sun's equator is tilted about 6.23 degrees from the invariable plane. This is the 6-degree tilt we've been discussing, small enough to suggest a common origin, but large enough to demand explanation. Measuring this tilt required centuries of astronomical observation and innovation. First, astronomers had to determine the Sun's rotation axis. This was done by tracking sunspots, those dark, relatively cool regions on the Sun's surface that appear, evolve, and disappear over days or weeks. By carefully following sunspots as they move across the sun's disk, astronomers could determine not just the period of the sun's rotation, but also the orientation of its rotation axis in space. This work began with Galileo's first telescopic observations of sunspots in 1612 and continues today with sophisticated solar telescopes both on Earth and in space. But sunspot observations alone aren't enough. The sun's differential rotation, the fact that it rotates faster at the equator than at the poles, complicates the picture. Moreover, sunspots don't appear uniformly across the sun's surface. They're concentrated in bands at mid-latitudes that migrate toward the equator over the 11-year solar cycle. Modern measurements of the sun's rotation use a technique called helioseismology, which studies sound waves travelling through the sun's interior. Just as seismologists use earthquake waves to probe Earth's interior, helioseismologists use the sun's natural oscillations to map its internal structure and rotation. These measurements have confirmed and refined our understanding of the sun's rotation axis. Determining the invariable plane required a different kind of observation, precise tracking of planetary positions over extended periods. Each planet's mass had to be determined along with its orbital parameters, the size and shape of its orbit, its inclination, and the direction of its angular momentum vector. This work began with naked eye observations by ancient astronomers, was revolutionized by the telescope, and reached new levels of precision with radar ranging and spacecraft tracking. Every planetary mission, from Mariner to Voyager to Cassini to Juno, has contributed to our understanding of planetary masses and orbits. The calculation itself is elegant in its simplicity, though the details can be computationally intensive. Each planet's angular momentum is computed as the product of its mass, its orbital velocity, and its distance from the Sun, with appropriate corrections for the elliptical shape of the orbit. These are vector quantities, having both magnitude and direction. The directions are perpendicular to each planet's orbital plane. When all these vectors are added together, the resulting sum points perpendicular to the invariable plane. The plane itself passes through the Sun. Since we're measuring orbital angular momentum around the Sun as the centre, it's worth pausing to appreciate the precision of these measurements. When we say the Sun's equator is tilted 6.23 degrees from the invariable plane, we're not guessing or approximating. This number comes from measurements accurate to a fraction of a degree, based on observations spanning centuries and refined by space-age technology. The fact that we can determine such subtle angles in a system spanning billions of kilometres is a testament to both the regularity of celestial mechanics and the ingenuity of human observers. But our solar system doesn't exist in isolation. It's part of the Milky Way galaxy, a vast disk of hundreds of billions of stars, and this gives us yet another reference plane to consider, the galactic plane. From our perspective on Earth, we see the galactic plane edge on as the band of the Milky Way across our night sky. This luminous river of stars marks the main disk of our galaxy, where most of its stars, gas and dust are concentrated. The galactic plane provides a reference frame for understanding our solar system's orientation within the larger cosmic context. Measuring our solar system's tilt relative to the galaxy requires us to know two things: the orientation of the galactic plane as seen from our position, and the orientation of our solar system's invariable plane. The first has been determined through centuries of star mapping, culminating in modern surveys like those conducted by the Gaia Space Telescope, which has measured the positions and motions of over 1 billion stars with unprecedented precision. The second we've already discussed. When we compare these two planes, we find that they're inclined to each other by about 60 degrees, a much larger angle than the 6-degree tilt within our solar system. This 60-degree angle means that our solar system is oriented quite differently from the galaxy's main disk. If you imagine the galaxy as a dinner plate and our solar system as a smaller plate, the solar system plate would be tilted up at a steep angle rather than lying flat within the larger plate. This orientation affects how we see the galaxy from Earth. Over the course of a year, as Earth orbits the Sun, our night sky looks out toward different parts of the galaxy. In June, we look toward the galactic centre in the constellation Sagittarius. In December, we look outward toward the galactic edge in the direction of Orion. The solar system's motion through the galaxy adds another layer of complexity to these angular relationships. We're not just tilted relative to the galaxy, we're moving through it at about 230 kilometers per second, completing an orbit around the galactic centre every 225 million years. But this motion isn't confined to the galactic plane. The solar system oscillates above and below the plane like a horse on a cosmic carousel, completing a full cycle every 60 million years or so. Currently, we're about 55 light-years above the galactic plane and moving upward. This oscillation is caused by the galaxy's gravity. Most of the galaxy's mass is concentrated in its disk, and this creates a gravitational pull that tends to draw objects toward the plane. When the solar system is above the plane, it feels a downward pull. When it's below, it feels an upward pull. Like a pendulum, it oscillates back and forth, though the motion is so slow that all of human history represents just a tiny fraction of one oscillation. Understanding these different reference frames and the angles between them helps us piece together the history and dynamics of our cosmic neighbourhood. The 6-degree tilt between the Sun and the invariable plane likely dates back to the solar system's formation, possibly reflecting asymmetries in the original protoplanetary disk or the influence of the Sun's birth environment. The 60-degree tilt relative to the galaxy might be inherited from the motion of the gas cloud from which our solar system formed, or it might have been acquired through gravitational interactions over billions of years. These measurements also have practical implications for space exploration and astronomy. When we send spacecraft to explore the solar system, we need to account for the various planes and their relationships. Missions to the outer planets often launch when Earth is positioned to take advantage of the target planet's orbital plane. The Voyager missions, for example, were timed to take advantage of a rare alignment of the outer planets that occurs only once every 175 years. Understanding the invariable plane helps mission planners calculate the most efficient trajectories for spacecraft navigating the solar system. For astronomers studying the universe beyond our solar system, understanding these angular relationships is crucial for interpreting observations. The solar system's tilt affects how we see the cosmic microwave background radiation, the afterglow of the Big Bang. It influences our view of distant galaxies and our ability to detect exoplanets. Even the search for dark matter is affected by our understanding of how the solar system is oriented and moving through space. There's something deeply satisfying about the way these measurements connect different scales of the universe. The 6-degree tilt we observe is a local phenomenon, a property of our immediate cosmic neighbourhood. But understanding it requires us to consider the galaxy as a whole, the formation of stars and planetary systems in general, and the fundamental laws of physics that govern angular momentum and gravity. Each measurement is a thread in a vast tapestry, and pulling on any thread reveals connections to the whole. As we delve deeper into these technical aspects, it's easy to get lost in numbers and angles, planes and vectors. But let's not forget the wonder that brought us here. Every one of these measurements represents countless hours of human observation, calculation, and contemplation. Behind every number is a story of curiosity and dedication, of people who looked up at the night sky and asked why. The 6-degree tilt isn't just a number, it's a puzzle that has engaged some of the brightest minds in history and continues to inspire new questions and investigations. Consider the patience required for these measurements. Some of them span centuries, with each generation of astronomers building on the work of their predecessors. The accurate determination of planetary masses and orbits required observations over many orbital periods. 164 years for Neptune, 248 years for Pluto. The discovery of the solar system's oscillation through the galactic plane required understanding patterns that play out over millions of years. This is science at its most patient and persistent, knowledge accumulated drop by drop over generations. And yet, despite all our measurements and calculations, mysteries remain. We still don't know exactly why the Sun is tilted relative to the planetary system. We can't say with certainty whether this tilt has changed over the solar system's history, or whether it will change in the future. We don't fully understand all the factors that determine a solar system's orientation when it forms. Each answer leads to new questions. Each measurement reveals new subtleties to explore. This is perhaps the most beautiful aspect of scientific inquiry. It's never really finished. The 6-degree tilt we're discussing tonight might seem like a simple fact, but it opens onto an infinite regress of questions. Why 6 degrees and not 5 or 7? How common is this amount of tilt among other solar systems? What would our solar system be like if the tilt were different? These questions don't have easy answers, and that's what makes them worth asking. As you continue to relax and perhaps drift closer to sleep, imagine yourself floating above the solar system, able to see all these planes and angles we've been discussing. There's the ecliptic, Earth's orbital plane, marked by our planet's annual journey around the Sun. There's the invariable plane, slightly different, defined by the combined angular momentum of all the planets. There's the Sun's equatorial plane, tilted those crucial 6 degrees, marked by the paths of sunspots across the solar surface. And far beyond, almost perpendicular to all of these, stretches the vast plane of the galaxy, that river of stars we call the Milky Way. From this cosmic vantage point, you can see how all these planes intersect and relate to each other. They're not rigid structures, but mathematical abstractions, ways of organizing our understanding of celestial motions. Yet they're also real in the sense that they reflect genuine physical relationships, actual constraints on how objects move through space. The planets really do orbit in nearly the same plane. The Sun really does rotate at an angle to that plane. The galaxy really does have a preferred orientation. These aren't human inventions, but discoveries, patterns in nature that existed long before we noticed them and will persist long after we're gone. The invariable plane, in particular, has a special significance that goes beyond its role as a reference frame. It represents the solar system's memory of its own formation. When that primordial cloud of gas and dust began to collapse, 4.6 billion years ago, it carried with it a certain amount of angular momentum. That angular momentum has been conserved ever since, passed from the collapsing cloud to the forming disk, from the disk to the planets, maintained through all the complex gravitational interactions and evolutionary changes the solar system has experienced. The invariable plane is the geometric expression of that conservation, a fossil of our origins written in the sky. This conservation of angular momentum is one of the fundamental principles of physics, as basic as the conservation of energy or momentum. It tells us that in the absence of external torques, a spinning or orbiting system will maintain its angular momentum forever. This is why the planets continue to orbit in the same direction they have since their formation, why the solar system maintains its orientation as it travels through the galaxy, why the 6-degree tilt persists across billions of years. Angular momentum is one of the universe's most reliable bookkeepers, maintaining its accounts with perfect accuracy across cosmic time. But the solar system isn't perfectly isolated. External torques do exist, though they're generally very small. The gravitational pull of passing stars can exert tiny torques on the solar system. The galaxy's tidal forces create their own subtle effects. Even the pressure of starlight from distant stars creates a minute force that, accumulated over billions of years, could in principle affect the solar system's orientation. These forces are so small that their effects are almost imperceptible, but they remind us that our solar system is connected to the wider universe, subject to influences from far beyond our local neighbourhood. Some astronomers have tried to calculate whether these external influences could account for the Sun's 6-degree tilt. Could the cumulative effect of stellar encounters over the solar system's lifetime have torqued the Sun away from perfect alignment? The calculations suggest that while such effects exist, they're probably too small to account for the full 6 degrees. More likely, the tilt is primordial, dating back to the solar system's formation or shortly thereafter. But the possibility remains open, another thread for future investigators to pull. There's also the fascinating possibility that the solar system's tilt has actually helped stabilize it over cosmic time. Some computer simulations suggest that a perfectly aligned system might be more vulnerable to certain kinds of instabilities. The slight misalignment between the Sun and the planets might actually help dampen potentially destructive resonances, keeping planetary orbits stable over billions of years. If this is true, our 6-degree tilt isn't a flaw, but a feature, a subtle geometric arrangement that has helped maintain the clockwork of our solar system since its beginning. As we consider these possibilities, we're drawn into one of the deepest questions in astronomy. How special is our solar system? When we look at other planetary systems around other stars, do we see similar 6-degree tilts? Or is our configuration unusual, perhaps even rare? The answer has implications for our understanding of planetary system formation, and potentially for the prevalence of life in the universe. If stable, slightly tilted systems like ours are common, that might increase the chances of finding Earth-like planets elsewhere. If our configuration is unusual, it might be one of the factors that has allowed life to flourish here. Recent observations of exoplanetary systems have revealed an astonishing diversity of configurations. We've found systems where planets orbit backwards, relative to their star's rotation, systems with wildly tilted orbits, systems that seem perfectly aligned, and everything in between. Some young stars show disks tilted at dramatic angles, while others appear well aligned. This diversity suggests that there's no single, universal pathway to planetary system formation. Each system's configuration depends on the specific conditions of its birth and evolution. The technique of measuring stellar obliquity, the angle between a star's rotation axis and its planet's orbital planes, has become increasingly sophisticated. One method involves observing the Rossiter-McLaughlin effect during planetary transits. When a planet passes in front of its star, it blocks first one side of the rotating star, then the other. This creates a characteristic pattern in the star's spectrum that reveals the angle between the star's rotation and the planet's orbit. Using this and other techniques, astronomers have measured obliquities for dozens of exoplanetary systems. What they've found is both encouraging and puzzling. Many systems show small obliquities similar to our solar system's 6 degrees, suggesting that modest misalignments might be common. But there are also plenty of exceptions, systems with obliquities of 30, 60, even 90 degrees or more. Hot Jupiters, those massive planets orbiting very close to their stars, show a particularly wide range of obliquities. This diversity tells us that whatever process creates tilts in planetary systems can produce a wide range of outcomes. The distribution of obliquities might hold clues to how planetary systems evolve. Systems that have experienced violent dynamical interactions, planet-planet scattering for instance, might show larger tilts. Systems that evolved more peacefully might maintain smaller tilts closer to their primordial values. By studying the statistics of tilts across many systems, astronomers hope to piece together the various pathways that lead from protoplanetary disks to mature planetary systems. Our own solar system's modest 6-degree tilt places it in what seems to be a fairly common category. Not perfectly aligned, but not dramatically misaligned either. This might be telling us something about our system's relatively peaceful history. While there's evidence for some planetary migration and dynamical evolution in our solar system's past, it seems to have avoided the kind of violent instabilities that would produce large obliquities. The 6-degree tilt might be a sign of our solar system's relative stability and orderly evolution. As we near the end of this second phase of our contemplation, let's return to the human dimension of these measurements. Every number we've discussed, the 6.223 degree tilt of the Sun, the 1.58 degree inclination of the invariable plane to the ecliptic, the 60 degree angle to the galactic plane, represents the culmination of human curiosity and ingenuity. These aren't numbers that nature handed to us directly. We had to work for them, developing instruments, techniques, and theories over centuries. Think about the first person who noticed that sunspots move across the sun's face in a regular pattern, revealing the sun's rotation. Think about the astronomers who spent years, decades even, tracking planetary positions to determine their orbits with sufficient precision to calculate the invariable plane. Think about the engineers who designed and built the spacecraft that have refined these measurements to extraordinary precision. Each of these people contributed to our understanding of that simple number, 6 degrees, and the work continues. Right now, as you listen to these words, telescopes on Earth and in space are gathering data that will further refine our measurements. The Gaia spacecraft is mapping the galaxy in 3 dimensions, giving us a better understanding of our orientation within it. The Solar Orbiter mission is studying the Sun from outside the ecliptic plane, providing new perspectives on our star's rotation and magnetic field. Future missions will undoubtedly reveal new subtleties, new questions, new wonders about our cosmic orientation. There's something profoundly hopeful about this ongoing investigation. Despite all the challenges facing humanity, we continue to look up, to wonder, to measure, to try to understand our place in the cosmos. The 6-degree tilt might seem like an abstract, even trivial detail, but our curiosity about it reflects something essential about human nature. The desire to understand, to find patterns and meaning in the universe around us. This curiosity doesn't pay the bills or solve immediate problems, but it feeds something deeper, our need to know who we are and where we are in the grand scheme of things. As we prepare to delve even deeper into the specifics of our solar system's orientation, examining the invariable plane in detail and exploring what makes it such a fundamental reference for understanding our cosmic neighborhood, let's pause once more to appreciate the elegance of what we've discovered. The solar system, for all its complexity, can be described with remarkable precision using just a few angles and planes. These geometric relationships encode the history of our cosmic neighborhood, from its birth in a collapsing cloud of gas to its current journey through the galaxy. The 6-degree tilt is just one thread in this geometric tapestry, but it's a thread that connects to everything else. Pull on it, and you find yourself exploring the formation of planetary systems, the dynamics of rotating bodies, the structure of galaxies, the conservation laws of physics. It's a number that seems simple, but opens onto infinite complexity, a measurement that seems precise but invites endless refinement and reinterpretation. This is the beauty of science. Even the simplest questions can lead us on journeys of discovery that span the cosmos and echo through time. The invariable plane deserves our deeper attention, for it is perhaps the most fundamental reference frame we have for understanding our solar system's architecture. Unlike the ecliptic, which is just Earth's orbital plane, or the Sun's equatorial plane, which reflects only our star's rotation, the invariable plane emerges from the collective motion of everything orbiting the Sun. It's as if all the planets got together and voted on what the solar system's true orientation should be, with each planet's vote weighted by its angular momentum. Jupiter, massive and distant, cast the deciding vote, but every world from Mercury to Neptune has its say. To truly appreciate what the invariable plane represents, we need to think about angular momentum not as an abstract concept but as something almost tangible, a kind of cosmic currency that can be exchanged but never created or destroyed. Picture each planet as carrying a certain amount of this rotational currency as it circles the Sun. Jupiter, that giant among worlds, holds about 60% of the planetary system's total angular momentum. Saturn accounts for about 25%. Uranus and Neptune together contribute about 14%. And all the terrestrial planets, Mercury, Venus, Earth and Mars combined, hold less than 1% of the total. This distribution tells us something profound. When we talk about the plane of the solar system, we're really talking about the plane defined by the giant planets. The mathematical beauty of the invariable plane lies in its stability. Individual planets can exchange angular momentum through gravitational interactions. Jupiter can tug on Saturn. Saturn can influence Uranus. Complex resonances can shift orbits over millions of years, but the total angular momentum remains constant. This means the invariable plane provides a fixed stage on which all the solar system's dynamical dramas play out. Planets may migrate, orbits may evolve, but the invariable plane endures, a constant in a cosmos of change. Let's imagine we could see angular momentum directly, perhaps as a soft glow emanating from each orbiting body. Jupiter would blaze like a cosmic lighthouse, its angular momentum vector pointing steadily perpendicular to its orbital plane. Saturn would shine with a somewhat dimmer but still brilliant light. The ice giants, Uranus and Neptune, would add their own steady glows, and there, barely visible in comparison, would be the faint whispers of light from the terrestrial planets, including Earth. If we were to add all these glowing vectors together, and remember, vectors have both magnitude and direction, the sum would point exactly perpendicular to the invariable plane. The discovery and calculation of the invariable plane represents one of the triumphs of celestial mechanics. It emerged from the work of Pierre-Simon Laplace in the late 18th century, who recognized that this plane would remain fixed even as individual planetary orbits evolved. Laplace called it the invariable plane precisely because of this stability. He understood that while planets could exchange angular momentum among themselves, the total had to be conserved, providing a fixed reference against which all changes could be measured. But Laplace could only approximate the invariable plane's orientation based on the limited observations available in his time. The masses of the outer planets were poorly known, and Uranus had only recently been discovered. Neptune was still unknown, lurking unseen in the outer darkness. Each improvement in our knowledge of planetary masses and orbits has refined our determination of the invariable plane. The Voyager missions, which flew by all 4 giant planets and measured their masses with unprecedented precision, significantly improved our knowledge of the invariable plane's exact orientation. Today, we know the invariable plane is inclined about 1.58 degrees to the ecliptic, with its ascending node, the point where it crosses the ecliptic from south to north, located at about 107 degrees longitude, in the direction of the constellation Cancer. These numbers might seem arbitrary, but they encode deep information about how angular momentum is distributed in our solar system. The fact that the inclination is small tells us that the planets all orbit in roughly the same plane, a sign of their common origin in a flat protoplanetary disk. The specific value and orientation tell us about the detailed distribution of mass and motion in our cosmic neighbourhood. The invariable plane also serves as a kind of fossil record of the solar system's formation. When that primordial disk of gas and dust surrounded our young sun, it had a certain orientation in space, a certain distribution of angular momentum. As planets formed and the gas dissipated, that angular momentum was preserved, locked into the orbits of the planets. The invariable plane we observe today is essentially the plane of that ancient disk, preserved across 4.6 billion years like a geometric fossil. This connection to our origins becomes even more fascinating when we consider what might have happened if things had been different. What if Jupiter had formed closer to the Sun, or farther away? What if we had no giant planets at all, or twice as many? Each alternative history would produce a different invariable plane, a different fundamental orientation for the solar system. The specific invariable plane we observe is unique to our particular configuration of planets, a geometric signature as distinctive as a fingerprint. Recent computer simulations have explored how the invariable plane might have evolved over the solar system's history. In the early days, when the protoplanetary disk still contained significant amounts of gas, the invariable plane would have been defined not just by the forming planets, but by the gas itself. As the gas dissipated, blown away by solar wind and radiation, the invariable plane would have shifted slightly to its current orientation. This shift would have been small, perhaps a degree or less, but it represents a real evolution in the solar system's fundamental reference frame. There's also the fascinating question of how the invariable plane relates to structures in the outer solar system. Beyond Neptune lies the Kuiper Belt, that vast ring of icy bodies that includes Pluto and thousands of other objects. Many Kuiper Belt objects orbit in or near the invariable plane, but others are dramatically inclined. Some theorists have suggested that the distribution of inclinations in the Kuiper Belt might preserve information about conditions in the early solar system, including possible close encounters with passing stars or the presence of additional planets that have since been ejected. The scattered disk, an even more distant population of icy bodies with highly elliptical and inclined orbits, tells another part of the story. These objects were likely scattered outward by gravitational encounters with Neptune, their orbits bearing witness to billions of years of dynamical evolution. Yet even these scattered objects in aggregate respect the invariable plane in subtle ways. Their orbital orientations aren't random, but show patterns that reflect the underlying architecture of the solar system. When we consider the Sun's 6-degree tilt relative to this invariable plane, we're really asking about the relationship between two different records of our solar system's birth. The invariable plane preserves the angular momentum of the protoplanetary disk, while the Sun's rotation preserves information about the angular momentum of the central region where our star formed. The misalignment between them suggests that these two regions weren't perfectly coupled, that something caused the inner and outer parts of the forming solar system to remember slightly different orientations. One possibility is that the Sun's rotation was influenced by magnetic fields in ways that didn't affect the planets. Young stars have powerful magnetic fields that can interact with the surrounding disk, transferring angular momentum and potentially causing tilts. If the Sun's magnetic field was misaligned with the disk, perhaps due to turbulence in the collapsing cloud or the influence of nearby stars, it could have torqued the Sun away from perfect alignment. This magnetic braking might explain not just the Sun's tilt, but also why it rotates relatively slowly compared to what we might expect. Another intriguing idea involves the possibility that the Sun had a companion star early in its history. Many stars form in binary or multiple systems, and it's possible that our Sun had a stellar sibling that was later ejected or drifted away. Such a companion could have gravitationally influenced the Sun's rotation or the orientation of the protoplanetary disk, leaving the 6-degree tilt as a kind of geometric scar from this ancient relationship. While there's no direct evidence for such a companion, the idea remains an active area of theoretical investigation. The invariable plane also plays a crucial role in our understanding of how the solar system interacts with its galactic environment. As our solar system orbits the center of the Milky Way, it encounters different regions of space with varying densities of stars, gas, and dark matter. These encounters can, in principle, exert torques on the solar system. But because angular momentum is conserved, these torques can't change the invariable plane directly. Instead, they might cause the entire solar system to precess, to slowly change its orientation in space while maintaining the same internal configuration. This precession would be incredibly slow, taking hundreds of millions or billions of years to complete even a small rotation. But over the lifetime of the solar system, such effects could accumulate. Some researchers have tried to calculate whether galactic torques could have contributed to the Sun's tilt or affected the orientation of the invariable plane. The calculations suggest these effects are probably small, but they remind us that our solar system isn't isolated. It's embedded in and influenced by the larger galactic environment. The concept of the invariable plane extends beyond our solar system to other planetary systems around other stars. Every system with multiple planets has its own invariable plane, its own fundamental reference defined by the distribution of angular momentum. By studying these planes in other systems, astronomers can learn about the diversity of planetary system architectures and the processes that shape them. Systems with planets in dramatically different planes might have experienced violent dynamical histories. Systems with well-aligned planets might have evolved more peacefully. The challenge is that measuring the invariable plane of an exoplanetary system is much harder than measuring it for our own solar system. We can't see most exoplanets directly, and we often know only about a subset of the planets in any given system. But as our detection methods improve, and we discover more complete planetary systems, we're beginning to piece together the three-dimensional architectures of these distant worlds. Each system's invariable plane tells a story about its formation and evolution, adding another chapter to our understanding of how planetary systems work. There's something deeply satisfying about the way the invariable plane connects the largest and smallest scales in our solar system. The orbits of the giant planets, spanning billions of kilometers, define a plane that remains stable down to fractions of a degree. This same plane influences the orbits of asteroids just a few kilometers across, the paths of comets that venture from the outer darkness, even the trajectories of the spacecraft we send to explore our cosmic neighborhood. It's a unifying principle that ties together the entire solar system into a coherent whole. Consider how this plays out in practical terms for space exploration. When mission planners design trajectories to the outer planets, they often take advantage of the fact that all the giant planets orbit close to the invariable plane. This means a spacecraft can visit multiple outer planets without requiring large changes in orbital inclination, which would be energetically expensive. The Voyager 2 spacecraft's grand tour of all 4 giant planets was possible, partly because they were arranged along a path close to the invariable plane. Future missions to explore the outer solar system will similarly benefit from understanding this fundamental geometry. The invariable plane also affects how we search for objects in the outer solar system, including the hypothetical Planet 9. If such a planet exists, its orbit would contribute to the total angular momentum of the solar system, slightly shifting the invariable plane from what we calculate based on the known planets. By looking for subtle discrepancies between the observed and calculated invariable plane, astronomers might find indirect evidence for undiscovered massive objects in the outer solar system. So far, no such discrepancies have been definitively identified, but the search continues. As we contemplate the invariable plane and its relationship to the Sun's rotation, we're really exploring one of the fundamental questions in astronomy. How much of what we observe is inevitable, and how much is contingent? Is the 6-degree tilt a necessary outcome of the physics of star and planet formation, something we should expect to see in most planetary systems? Or is it a historical accident, the result of random events during our solar system's birth that could easily have been different? The answer probably lies somewhere in between. The physics of angular momentum conservation means that some misalignment between stars and their planetary systems is likely common, perhaps even inevitable, given the chaotic nature of star formation. But the specific value, 6 degrees rather than 5 or 7 or 20, probably depends on the detailed history of each system. Our solar system's 6-degree tilt is both typical and unique, an example of a universal process that produces diverse outcomes. This brings us to a deeper philosophical point about the nature of scientific explanation. When we ask why the solar system is tilted 6 degrees, we're seeking a causal explanation, a story about events and processes that led to this specific configuration. But perhaps the question itself reveals an assumption, that there should be a special reason for this particular angle. Maybe 6 degrees is simply what emerged from the complex interplay of countless factors during the solar system's formation, no more in need of special explanation than the exact number of craters on the moon, or the precise shape of a particular cloud. Yet even if the specific value is contingent, understanding the processes that produce such tilts teaches us about the fundamental physics of planetary systems. Every measurement we make, every angle we determine, adds to our understanding of how angular momentum works, how gravitational interactions shape orbits, how magnetic fields influence rotating bodies. The 6-degree tilt becomes a window into these deeper principles, a specific example that illuminates general truths. As you continue to drift towards sleep, perhaps feeling the gentle pull of gravity holding you to Earth, remember that you're part of this vast system of angular momentum we've been discussing. Earth's rotation contributes its small share to the invariable plane. Every orbit our planet completes adds another cycle to the billions that have come before, maintaining the patterns established when the solar system was young. You're not just an observer of this cosmic dance, you're a participant, carried along by the same conservation laws that keep the planets in their courses. The invariable plane isn't just a mathematical abstraction or a convenience for astronomers. It's a real thing in the sense that it reflects genuine physical constraints on how objects move in our solar system. It's the averaged out memory of our origins, the geometric ghost of the protoplanetary disk, the stage on which all solar system dynamics play out, and the fact that our sun is tilted 6 degrees from this plane isn't a flaw or an error. It's a clue, a piece of evidence about our history, a thread that connects us to the tumultuous birth of our cosmic home. Now, as we turn our attention to the sun itself, to understand more deeply what it means for our star to be tilted relative to its planetary system, we enter into one of the most intimate aspects of this mystery. The sun, after all, isn't just another celestial body. It's the source of all energy that drives life on Earth, the gravitational anchor of our solar system, the star whose light defines our days and whose warmth makes our planet habitable. Understanding its tilt means understanding something fundamental about the star that makes our existence possible. The sun's rotation is a wonder in itself, quite apart from its tilt. Our star doesn't rotate as a solid body would. Instead, different latitudes rotate at different rates, a phenomenon called differential rotation that's possible because the sun is made of plasma, not solid matter. At the equator, the sun completes a rotation in about 25 days. At latitudes of 60 degrees, the rotation period stretches to about 29 days. Near the poles, it takes even longer, about 35 days. This differential rotation is like watching a cosmic river where the current flows at different speeds across its width. This complex rotation pattern is driven by the interplay of convection and rotation in the sun's interior. Deep inside, in the radiative zone, the sun likely rotates more or less as a solid body. But in the outer convection zone, where hot plasma rises and cool plasma sinks in vast cells, the rotation becomes differential. The boundary between these zones, called the tachocline, is thought to be where the sun's magnetic field is generated through a process called the solar dynamo. This magnetic field, in turn, drives the 11-year solar cycle of sunspots and solar activity that affect space weather throughout the solar system. Measuring the sun's rotation and determining its axis orientation has been a centuries-long endeavour. Galileo was among the first to track sunspots and notice their regular motion across the solar disk. But sunspots are imperfect traces of rotation. They appear and disappear, they have their own proper motions, and they don't appear at all latitudes. Modern measurements use multiple techniques to build a complete picture of solar rotation. Helioseismology studies sound waves propagating through the sun's interior, Doppler measurements track the motion of the solar surface, and observations of coronal features reveal rotation patterns in the sun's atmosphere. The precision of these modern measurements is extraordinary. We can now detect variations in the sun's rotation rate of less than 1%, map how rotation varies with depth inside the sun, and track changes in rotation patterns over the solar cycle. These observations have revealed that the sun's rotation is even more complex than previously thought, with bands of faster and slower rotation called torsional oscillations that migrate toward the equator over the course of the solar cycle. Yet through all this complexity, the sun's rotation axis remains remarkably stable, maintaining its 6-degree tilt relative to the invariable plane. But why should the sun be tilted at all? To understand this, we need to go back to the beginning, to the collapsing cloud of gas and dust from which our solar system formed. In the standard model of star formation, a rotating cloud collapses under its own gravity, spinning faster as it contracts due to conservation of angular momentum. The cloud flattens into a disk, with a protostar forming at the center and planets eventually forming in the disk. If this process were perfectly smooth and symmetrical, we might expect the star's rotation axis to align perfectly with the disk's axis and thus with the eventual invariable plane of the planetary system. But star formation is anything but smooth and symmetrical. It's a chaotic process, full of turbulence, magnetic fields, and asymmetric flows. Gas doesn't fall smoothly onto the forming star but arrives in streams and clumps. The protostar doesn't grow steadily, but in bursts of accretion. Magnetic fields thread through the collapsing cloud, channeling gas along field lines and potentially twisting the flow. In this chaotic environment, it would be surprising if the star's rotation ended up perfectly aligned with the surrounding disk. Recent observations of young stellar systems have confirmed this picture. Using instruments like ALMA, astronomers have imaged protoplanetary disks around young stars and found that misalignments are common. Some disks are warped or broken into sections tilted at different angles. Some show evidence of misalignment between the inner and outer disk. In some cases, we can even measure the star's rotation and confirm that it's tilted relative to the disk. These observations suggest that the 6-degree tilt we see in our solar system might have been established very early, perhaps within the first million years of the Sun's life. One particularly intriguing mechanism for creating stellar obliquity involves magnetic interactions between the young star and its disk. Young stars have powerful magnetic fields, thousands of times stronger than the Sun's current field. These fields can connect the star to the surrounding disk, creating magnetic bridges along which gas flows onto the star and angular momentum is exchanged. If the magnetic field is misaligned with the disk, which is likely given the chaotic nature of star formation, it can torque the star's rotation away from alignment with the disk. This magnetic star-disk interaction might not only explain the Sun's tilt, but also why the Sun rotates relatively slowly compared to theoretical predictions. Another possibility involves gravitational interactions in the Sun's birth environment. Stars typically form in clusters, and our Sun was likely born with hundreds or thousands of siblings in a stellar nursery. In such a crowded environment, close encounters between stars or their protoplanetary disks would have been common. A passing star could gravitationally perturb the Sun's disk, warping it, or changing its orientation. If this happened early enough, while the Sun was still accreting and its rotation axis was still being established, it could have led to the misalignment we observe today. There's even the possibility that the Sun's tilt was influenced by infalling material after the main phase of disk formation. If a late-arriving clump of gas fell onto the disk or the star from a different direction than the main accretion flow, it could have changed the system's angular momentum distribution. This kind of late accretion is observed in some young stellar systems and might be more common than previously thought. Each infalling clump would be like a cosmic curveball, potentially shifting the star's rotation or the disk's orientation. The 6-degree value itself might hold clues to which mechanism was responsible. Some processes tend to produce small tilts, others large ones. Magnetic star-disk interactions typically produce tilts of a few degrees to tens of degrees, consistent with what we observe. Gravitational perturbations from passing stars could produce a wide range of tilts, depending on the encounter parameters. Late infall could produce small or large tilts, depending on the amount and direction of infalling material. The modest 6-degree tilt we observe suggests a relatively gentle process, not a violent disruption. Interestingly, the Sun's tilt might actually have helped stabilize the solar system over its long history. Computer simulations suggest that some resonances between planetary orbits and stellar rotation can lead to instabilities over billions of years. A small misalignment between the star and the planetary system can prevent these resonances from forming or weaken their effects. In this view, the Sun's 6-degree tilt isn't an imperfection, but a stabilizing feature that has helped maintain the regular clockwork of planetary orbits over the age of the solar system. The Sun's tilt also affects how we observe solar phenomena from Earth. As Earth orbits the Sun, our viewing angle of the solar rotation axis changes, causing us to see more of the Sun's north pole at some times of year and more of the South Pole at others. This changing perspective, called the B angle, varies by about +2 7.25 degrees over the course of a year. It affects how we see sunspots, solar flares, and coronal mass ejections. It also means that some regions of the Sun are better observed at certain times of year, influencing the planning of solar observations and space weather monitoring. The tilt becomes even more important when we consider the three-dimensional structure of the Sun's magnetic field and the solar wind. The Sun's magnetic field isn't a simple dipole like Earth's, but has a complex structure that changes over the solar cycle. This field is carried outward by the solar wind, creating the heliosphere, the vast magnetic bubble that surrounds our solar system. The tilt of the Sun's rotation axis means that the heliospheric current sheet, the surface where the Sun's magnetic field changes polarity, is warped like a ballerina's skirt. As Earth orbits the Sun, we pass above and below this current sheet, experiencing different magnetic polarities and solar wind conditions. Space missions have given us unprecedented views of the Sun's rotation and its effects. The Ulysses spacecraft, which flew over the Sun's poles, revealed how the solar wind varies with solar latitude. The Solar and Heliospheric Observatory, SOHO, has monitored the Sun continuously for over 2 decades, tracking its rotation and activity. The Solar Dynamics Observatory provides high-resolution images of the entire solar disk, allowing us to study rotation and magnetic activity in exquisite detail. The Parker Solar Probe is now flying closer to the Sun than any previous spacecraft, directly sampling the solar wind and magnetic field in regions where they're still being accelerated and shaped by solar rotation. These observations have revealed subtle variations in the Sun's rotation that might be related to its tilt. For instance, there's evidence that the Sun's rotation axis itself might precess slightly, wobbling like a top over very long timescales. This precession would be caused by the gravitational pull of the planets on the Sun's oblate shape. The Sun is slightly flattened by its rotation, and this departure from perfect sphericity allows planets to exert small torques. The effect is tiny, but over millions of years it could cause measurable changes in the Sun's orientation. There's also the fascinating question of whether the Sun's tilt has changed over its lifetime. When the Sun was young, it rotated much faster than it does today, perhaps completing a rotation in just a few days rather than the current 25 days. This faster rotation would have made the young Sun more oblate, potentially making it more susceptible to gravitational torques from forming planets. As the Sun spun down over billions of years, losing angular momentum through its magnetized solar wind, its shape would have become more spherical, and its response to planetary torques would have changed. The 6-degree tilt we observe today might be different from the tilt billions of years ago. Some researchers have tried to use the Sun's current tilt to work backwards and understand conditions in the early solar system. If we know the current tilt and can model all the processes that might have affected it over 4.6 billion years, we might be able to constrain what the initial conditions must have been. This is like archaeological detective work, using present-day evidence to reconstruct ancient events. The challenge is that many different scenarios could lead to the same present-day configuration, making it difficult to uniquely determine what happened. The Sun's tilt also connects to broader questions about stellar evolution and planetary habitability. Stars with different tilts might have different patterns of magnetic activity, different solar wind properties, different space weather environments. These variations could affect the habitability of planets, influencing atmospheric erosion, radiation exposure, and climate stability. Understanding the relationship between stellar obliquity and planetary habitability could help us identify which exoplanetary systems are most likely to host life. As we observe more exoplanetary systems and measure more stellar obliquities, we're building a statistical picture of how common or unusual our Sun's 6-degree tilt might be. Preliminary results suggest that small to moderate obliquities like the Sun's are fairly common, at least for systems with planets similar to those in our solar system. This is encouraging for the search for Earth-like planets, as it suggests that the relatively stable, orderly configuration of our solar system might not be rare. But there are still many unknowns. We don't fully understand all the processes that can create or modify stellar obliquity. We don't know whether obliquity typically remains constant over a star's lifetime or evolves significantly. We don't know whether there's a connection between stellar obliquity and the likelihood of forming Earth-like planets. Each new observation, each new theoretical insight adds another piece to this cosmic puzzle. The Sun's 6-degree tilt reminds us that even our nearest star, the one we know best, still holds mysteries. We can measure the tilt with exquisite precision, but explaining it requires us to reach back to events that occurred before Earth existed, to processes we can't directly observe, to physics that we're still working to understand. It's a humbling reminder of how much we still have to learn about the cosmos, even in our own backyard. Yet it's also inspiring to realize how much we have learned. The fact that we can measure a 6-degree tilt in a star 150 million kilometers away, that we can track its rotation with precision better than 1%, that we can model the complex interactions that might have produced this tilt billions of years ago, this is a testament to human curiosity and ingenuity. Each generation of astronomers has built on the work of their predecessors, gradually assembling our understanding of the Sun and its place in the solar system. As you continue to relax, perhaps imagining the Sun slowly rotating in space, tilted those 6 degrees from the plane of the planets, remember that this tilt is part of what makes our solar system unique. It's one of countless details that, taken together, create the specific cosmic environment in which we live. The tilt affects the solar wind that Earth experiences, the space weather that our technology must withstand, even the way sunlight falls on solar panels in space. It's a number that seems abstract but has real consequences for our world. Now, as we prepare to explore our solar system's motion through the galaxy and how our local tilt relates to the vast disk of stars we call home, let's pause to appreciate the intimate connection between the Sun's rotation and life on Earth. Every day, as the Sun rises and sets, as its light warms our planet and drives our weather, we're experiencing the effects of a star tilted 6 degrees from its planetary system. It's a tilt we usually don't notice, but it's always there, a constant geometric fact underlying the rhythms of our world. The transition from thinking about our solar system in isolation to seeing it as part of the galaxy requires a tremendous leap in scale. If the solar system were shrunk to the size of a dinner plate, the Milky Way would still be larger than Earth itself. Yet despite this vast difference in scale, the same physical principles apply. Angular momentum is conserved, gravity follows the same inverse square law, and reference frames can be defined and related to each other. The 6-degree tilt between the Sun and the invariable plane is mirrored, in a sense, by the much larger 60-degree tilt between our solar system and the galaxy. Our galaxy, the Milky Way, is a vast spiral of hundreds of billions of stars, and we see it edge on from our position within it. On a clear dark night, far from city lights, you can see the galaxy as a luminous band across the sky, a river of light that has inspired wonder and mythology throughout human history. This band marks the galactic plane, the disk where most of the galaxy's stars, gas and dust are concentrated. It's our cosmic city, and like any city, it has a structure, a layout, neighborhoods, and traffic patterns. Our solar system is like a single house in this vast metropolis, oriented at its own angle, following its own path through the galactic suburbs. The Milky Way is about 100,000 light-years in diameter, but only about 1,000 light-years thick in the disk where we reside. This makes it incredibly flat. If the galaxy were shrunk to the size of a vinyl record, it would be thinner than the record itself. This flatness tells us something fundamental about how galaxies form and evolve. Like our solar system, the galaxy's disk shape results from the conservation of angular momentum during gravitational collapse. But while our solar system formed from a single collapsing cloud, the galaxy formed from the merger and accretion of countless smaller systems over billions of years. Our Sun orbits the galactic center at a distance of about 26,000 light-years, in what astronomers sometimes call the galactic suburbs, not too close to the crowded, dangerous galactic center with its supermassive black hole and intense stellar density, and not too far out in the sparse galactic hinterlands. This location, in a relatively quiet region between spiral arms, might be one of the factors that has allowed life to develop and persist on Earth. Too close to the center, and we'd be exposed to more supernovae, more gravitational disruptions, more intense radiation. Too far out, and there might not have been enough heavy elements to form rocky planets like Earth. The solar system's 60-degree tilt relative to the galactic plane means we're oriented quite differently from the galaxy's overall rotation. If you could stand outside the galaxy and watch, you'd see the solar system moving through space like a frisbee thrown at an angle. maintaining its orientation as it orbits the galactic centre. This might seem strange. Why isn't our solar system aligned with the galaxy? The answer lies in the chaotic history of star formation and the fact that the galaxy isn't a rigid structure, but a collection of billions of individual systems, each with its own orientation. Stars form from giant molecular clouds, vast aggregations of gas and dust that can span hundreds of light years. These clouds have their own random motions and orientations within the galaxy. When a portion of such a cloud collapses to form stars, the resulting stellar systems inherit the angular momentum of their parent cloud region, not necessarily that of the galaxy as a whole. It's like raindrops forming from a cloud. Each drop falls in roughly the same direction, but with its own slight variations in trajectory. Moreover, the Milky Way has grown through cosmic mergers and acquisitions, absorbing smaller galaxies and star clusters over its history. Each merger brings in stars with different orbital orientations, adding to the diversity of stellar motions we observe. Our Sun might have formed from gas that was already orbiting at an angle to the galactic plane, or it might have been gravitationally perturbed into its current orientation by encounters with molecular clouds or spiral arms. The 60-degree tilt is our particular inheritance from this complex history. The solar system's motion through the galaxy isn't a simple circular orbit. We're currently moving at about 230 kilometers per second relative to the galactic center, completing one orbit every 225 million years. But superimposed on this circular motion is a vertical oscillation. Like a horse on a cosmic carousel, we bob up and down relative to the galactic plane. Currently, we're about 55 light-years above the plane and moving upward at about 7 kilometers per second. We'll continue rising for about another 14 million years, reaching a maximum height of about 250 light-years above the plane before gravity pulls us back down. This oscillation has a period of about 60 to 70 million years. We cross the galactic plane roughly every 30-35 million years. Some researchers have suggested that these plane crossings might correlate with events in Earth's history, such as mass extinctions or increased impact rates from comets. The idea is that when we pass through the denser galactic plane, we're more likely to encounter molecular clouds or have comets in the Oort cloud gravitationally perturbed. However, the evidence for such correlations remains controversial, and many factors besides our galactic position influence Earth's history. The solar system's tilt and motion through the galaxy also affects our view of the universe. Because we're tilted 60 degrees to the galactic plane, we get a relatively clear view of the extragalactic universe in some directions. The galactic disk blocks our view in the direction of the Milky Way band, creating what astronomers call the zone of avoidance, where distant galaxies are hidden behind our own galaxy's stars and dust. But perpendicular to the disk, we can see deep into space, observing galaxies billions of light-years away. Our tilted vantage point is like having a window that's partially blocked by a curtain. We can't see everything, but what we can see is spectacular. This cosmic perspective has been hard-won through centuries of observation and deduction. Ancient astronomers saw the Milky Way but didn't know what it was. It wasn't until the 20th century that we understood we're inside a galaxy, and only in recent decades have we been able to map our position and motion accurately. The Hipparcos satellite in the 1990s measured precise distances to thousands of nearby stars, allowing us to determine our motion through space. The Gaia mission, launched in 2013, has measured the positions and motions of over 1 billion stars, creating an exquisitely detailed map of our galactic neighbourhood. These observations have revealed that the solar neighbourhood is full of stellar streams and moving groups, associations of stars that share common motions through space. Some of these are the remnants of dissolved star clusters, others are the debris of small galaxies that the Milky Way has absorbed. Our Sun doesn't belong to any known stream or group. It seems to be a field star, pursuing its own path through the galaxy. But we're constantly passing through regions with different stellar populations, different ages, different chemical compositions. The galaxy's spiral arms add another layer of complexity to our journey. These arms aren't solid structures but density waves, regions where stars and gas are temporarily more concentrated. As we orbit the galaxy, we pass through spiral arms roughly every 100 million years. Currently, we're in a relatively quiet region between major arms, in what's sometimes called the local spur or Orion arm, a minor feature between the major Perseus and Sagittarius arms. our passage through spiral arms might affect the solar system in various ways, from increased cosmic ray exposure to gravitational perturbations of the Oort cloud. The interstellar medium through which we travel is far from empty. It contains gas, dust, magnetic fields, and cosmic rays. The density and properties of this medium vary considerably from place to place. Right now, the solar system is travelling through what's called the local interstellar cloud, a warm, relatively dense region, about 30 light-years across. In about 10,000 years, we'll exit this cloud and enter a different interstellar environment. These changes in our galactic environment happen on timescales much longer than human history, but much shorter than the age of the solar system. The sun's motion through this interstellar medium creates the heliosphere, a vast magnetic bubble that partially shields the solar system from galactic cosmic rays. The heliosphere is shaped by the balance between the outward pressure of the solar wind and the inward pressure of the interstellar medium. Because of our motion through space, the heliosphere is compressed in the direction of motion and extended in the opposite direction, like a cosmic teardrop or windsock. The Voyager spacecraft have crossed the boundary of the heliosphere, giving us our first direct measurements of the interstellar medium. Our tilted orientation affects how the heliosphere interacts with the interstellar medium. The angle between the solar system's motion through space and the sun's rotation axis, combined with the tilt of the planetary orbits, creates a complex three-dimensional structure. The heliospheric current sheet, warped by the sun's tilt, rotates as we move through space, creating a spiral pattern like a cosmic lawn sprinkler. This geometry affects how cosmic rays enter the solar system and how the solar wind interacts with the interstellar medium. The discovery of our solar system's orientation and motion through the galaxy has profound implications for our understanding of our cosmic context. We're not at the center of anything, not the solar system, not the galaxy, not the universe. We're tilted, moving, constantly changing our position and orientation in space. Yet this isn't a demotion, but a promotion to membership in a vast, dynamic cosmos. We're part of the galactic ecosystem, influenced by and influencing our cosmic environment. Consider what it means that we can determine these orientations and motions at all. We're organisms that evolved on the surface of one small planet, with sensory systems adapted for survival in a terrestrial environment. Yet we've developed the tools and techniques to measure our orientation in the galaxy, to track our motion through space, to understand our place in the cosmic order. The 6-degree tilt of our sun, the 60-degree tilt of our solar system, these aren't just numbers but achievements of human understanding, hard-won knowledge about our place in the universe. The relationship between these different tilts, the sun's tilt relative to the planets, the solar system's tilt relative to the galaxy, might not be coincidental. Some theorists have suggested that there might be preferred orientations for forming solar systems, angles that result naturally from the physics of star formation in galactic disks. If this is true, surveys of stellar obliquities and planetary system orientations in different parts of the galaxy might reveal patterns, preferred angles that reflect underlying physical processes. There's also the question of whether our tilts are typical or unusual. As we observe more planetary systems and measure their orientations relative to their host galaxy, we're building a statistical picture of cosmic geometry. Early results suggest a wide diversity of orientations with no strong preference for alignment or misalignment. This diversity might be telling us that star formation is inherently chaotic, that the specific orientation of each system is largely random, determined by local conditions rather than galactic-scale processes. The study of our solar system's orientation in the galaxy connects to fundamental questions in cosmology. How do galaxies form and evolve? How do stars and planetary systems form within galaxies? How common are planetary systems like ours? Each measurement of tilt and orientation provides a data point for testing theories of cosmic evolution. Our solar system's specific configuration, the 6-degree solar tilt, the 60-degree galactic tilt, becomes part of the larger story of how structure forms in the universe. As we continue to drift through space, our tilts slowly evolving under the influence of gravitational torques and tidal forces, we carry with us the history of our formation. The 6-degree tilt of the Sun is a fossil from our birth in a collapsing cloud of gas 4.6 billion years ago. The 60-degree tilt relative to the galaxy reflects the angular momentum of that primordial cloud, itself inherited from the chaotic dynamics of the galactic disk. These tilts are our geometric DNA, encoding information about where we came from and what we've experienced. Looking forward, our tilts will continue to evolve, though very slowly. Gravitational interactions with passing stars, encounters with molecular clouds, the slow precession induced by galactic tides, all these will gradually modify our orientation in space, but the changes will be tiny, measured in fractions of degrees over millions of years. For all practical purposes, the tilts we observe today will persist far into the future, a stable geometric framework for the continued evolution of our solar system. There's something deeply peaceful about contemplating these vast timescales and slow changes. While human history unfolds in years and decades, while civilizations rise and fall in centuries and millennia, the cosmic tilts we've been discussing evolve over millions and billions of years. They provide a kind of cosmic stability, a geometric foundation that remains essentially unchanged throughout all of human existence. The 6-degree tilt was there when life first emerged from the oceans, when dinosaurs walked the earth, when humans first looked up at the stars and wondered what they were. As you rest tonight, perhaps beginning to feel the gentle approach of sleep, you're lying at a particular angle in space, on a planet tilted 23.5 degrees, orbiting a star tilted 6 degrees, in a solar system tilted 60 degrees to the galaxy. These nested tilts, these angles within angles, define your orientation in the cosmos. You're not just somewhere, you're pointed in a particular direction, part of a specific geometric configuration that has been maintained for billions of years and will continue for billions more. The journey through space continues even as you rest. Right now, as you listen to these words, you're moving at 230 kilometers per second around the galaxy, rising at 7 kilometers per second above the galactic plane, spinning at up to 1600 kilometers per hour with Earth's rotation. Yet you feel perfectly still, held in the reference frame of Earth, experiencing what physicists call the equivalence principle, the inability to distinguish between being at rest and being in uniform motion. This is the profound relativity of motion, the fact that every reference frame is equally valid,